Today, we are solving LeetCode 1888, minimum number of flips to make the binary string alternating. Before we get into the actual problem, let's start with a short analogy. If you'd prefer to skip it, you can move to the next timestamp where we begin the problem directly. There is a moment in Attack on Titan where the scouts finally reach Grisha Yeager's basement. Inside that basement, they discover records explaining the truth about the world outside the walls. After seeing those records, Eren Yeager realizes something important. The situation is not infinitely complicated. There are essentially two possible sides. You are either aligned with Eldia or aligned with Marley. At that point, Levi Ackerman simplifies the reasoning. Instead of trying to analyze every possible outcome, the approach becomes straightforward. Compare reality with the two possible structures and choose the one that requires the least change. That exact idea is what we will apply in this problem. Now moving to the actual problem. We are given a binary string. Two operations are allowed. The first operation is rotation, which means moving the first character of the string to the end. The second operation is flip, where 0 becomes 1 or 1 becomes 0. Our goal is to convert the string into an alternating binary string using the minimum number of flips. An alternating binary string looks like 0101001 and so on, or 101010 and so on. Now, when reading the question, a few words stand out. The word rotation immediately suggests that the string behaves like a circular structure. For circular problems, a common trick is duplicating the string by writing s plus s. That allows us to simulate every possible rotation. The problem also asks us to choose the best rotation, which usually suggests a sliding window approach. And since we want the minimum number of flips, what we are really counting are mismatches between the current string and the desired alternating pattern. So combining these observations, the approach becomes sliding window on the duplicated string while counting mismatches against alternating patterns. Now, the key observation here is that an alternating binary string can only have two possible patterns. The first pattern starts with 0 and looks like 010101. The second pattern starts with 1 and looks like 101010. So instead of trying many different configurations, we only compare our string with these two patterns. The remaining complication is rotation. If the string length is n, then there are n possible rotations. Instead of rotating the string repeatedly, we duplicate it. For example, suppose the string is 1111000. The length of the string is 6. When we duplicate the string, we get 1111000111000. Now, every possible rotation appears as a window of length 6 inside this duplicated string. So we simply slide a window of size 6 across this duplicated string and compute the mismatch cost for each window. Now let's walk through this example step by step. Our original string is 1111000. The length of the string is 6. After duplicating the string, we get 1111000111000. We begin with the first window, which covers the first 6 characters. That window is 1111000. Now we compare this window with the alternating pattern that starts with 0, which is 010101. When we compare position by position, we see mismatches at 4 positions. That means 4 flips would be needed to convert this window into that pattern. Next, we compare the same window with the pattern that starts with 1, which is 101010. In this case, the mismatches occur at 2 positions. That means 2 flips are needed. Since we want the minimum number of flips, the best answer so far becomes 2. Now we slide the window one step forward. The new window becomes 1100001. Again, we compare it with the pattern starting with 0 and count the mismatches. That comparison gives 4 mismatches. Then we compare it with the pattern starting with 1 and get 2 mismatches. Since the minimum flips are still 2, our answer does not change. Now we slide the window again. The new window becomes 100011. Comparing with the first pattern gives 4 mismatches, and comparing with the second pattern gives 2 mismatches. So the best answer remains 2. Sliding the window again gives the substring 000111. When we compare this window with the 2 patterns, we again get 4 mismatches for the first pattern and 2 mismatches for the second pattern. The answer remains 2. Sliding again gives 0, 0, 1, 1, 1, 0. Once again, we see 4 mismatches for the first pattern and 2 mismatches for the second pattern. The answer is still 2. Finally, the last window becomes 0, 1, 1, 0, 0. After comparing with both alternating patterns, the minimum flips required for this window are again 2. At this point, we have checked every possible rotation. The minimum number of flips required to make the string alternating is 2. Now that the idea is clear, let's talk about how we implement this in code. First, we compute the length of the string. Then we create the duplicated string by concatenating the string with itself. This allows us to simulate all possible rotations. Next, we maintain a mismatch counter for the alternating pattern that starts with 0. As we scan through the duplicated string, we determine what character we expect at each position according to that pattern. If the actual character does not match the expected one, we increase the mismatch count. At the same time, we maintain a sliding window of length n. When the window moves forward, the leftmost character leaves the window, so we remove its mismatch contribution. Once the window size reaches n, we know we are evaluating one possible rotation of the string. At that point, we compute the mismatch count for the second alternating pattern. Instead of recalculating it from scratch, we observe that if a position matches the first pattern, it must mismatch the second pattern. So the mismatch count for the second pattern is simply n minus the mismatch count of the first pattern. We then update the answer with the minimum flips required for that rotation. By sliding this window across the duplicated string, we evaluate every rotation efficiently. Finally, let's look at the complexity. We scan the duplicated string once, so the time complexity is linear in terms of the length of the string. The extra space used for the duplicated string is also linear. And that's the complete idea behind this problem. Thanks for watching. If this helped, consider liking, commenting, subscribing, and sharing. TATAKAE.